Okay, so in this last video, we are going to introduce our last new tool for our recursive tool chain, which is in the step 2 for asymptotic analysis. So remember, in the last video, we came up with a recurrence, which just describes our runtime as a function, but a function that's a little complex and defined in terms of itself. And it wasn't very clear how we could take that function and turn it into an asymptotic bound. And so that's what we're going to be doing in this video, talking about asymptotic analysis. So when you have one of these recurrences and you want to turn it into a big theta bound, it's really hard to just look at it and know the answer. It's not like our simple case where we had a simple polynomial and you could just drop all lower order terms and constants. That process is not going to work here because these formulas are just a little bit more complex. So don't worry, we don't have to do anything incredibly time-consuming on our own for these types of problems because some mathematicians have some formulas that we can use. They looked at a lot of these recurrences and saw some patterns, and they kind of humbly came up with the master theorem that tells you for pretty much any recurrence of particular forms, how you can figure out what its asymptotic bound is. So the master theorem looks weird when you first see it. You do not need to worry about why it's true, like why this works to find these bounds. It involves a lot of proofs that we are just not able to do in this class. And it looks really complex at first, but it really does have a simple process that we'll walk through. And I think you will appreciate, it's hard to appreciate why this process is useful. When I had to learn these recurrences, my teacher decided not to teach us master theorem, which has been around for a little while. But we ended up having to have this gigantic table of different recurrences and look at what the runtime was, the asymptotic bound was. So you usually had to memorize like 20 different things. But for master theorem, it's relatively straightforward once you've practiced it a few times. So here's how master theorem works. Master theorem works for a type of recurrence that looks like this. It says it's going to be has some like base case where it's a constant amount of work d if n is at most some constant value. So that's like in our example, we have 2 if n is less than 3. And then in your recursive case, it's in the form of some constant a times t of n divided by b plus some function in terms of n. And so in our case, you could see that constant a is going to be something like 2. The constant b is something like 3 because we're doing n divided by 3. So this b here is 3. And then our function in terms of n is just that plus n non-recursive work. So that's what that f of n is trying to capture. And so what Master's theorem says is if your recurrence looks like this, then we can tell you what the big theta asymptotic bound is if you compare some of those constants. So the constants of interest are the constants a, b, and c. Now I haven't shown you what c is. C is a constant that describes your function, your non-recursive work. So we're going to look at this non-recursive work and find an asymptotic bound for just that non-recursive work. So in our example, that function is just plus n, and so we're going to bound that by big theta of n. And the c is going to be the power that n is raised to. So in our context, in this example, c is going to be 1. So again, constant a is the value in front of the t. Constant b is what you're dividing by at each time. And constant c is a bit hidden. It's the runtime polynomial, or the polynomial degree of that non-recursive work runtime. So listen, that's a lot of stuff. But then master theorem is pretty straightforward after that when you just compute a couple values. So it's all about the relationship between a, b, and c, those constants we just identified. And master theorem says if log base b of a is less than c, then t is going to be big theta of n to the c. If log base b of a is equal to c, then it's going to be big theta of n to the c log n. In our third and final case, log base b of a is greater than c, t of n is going to be n to the log base b of a. This a lot of math and formulas there, but the really nice thing is you just have to identify what these 3 constants are, plug in a couple pieces of math, and it just tells you what the answer is. You don't have to do any process of like doing proofs or anything like that. So let's do a concrete example here with our numbers. So I kind of already walked through identifying those constants A, B, and C for our example up on the top left. A is 2 because of the 2 in front of the t, B is 3 because that's what we're dividing by, and C is 1 because our non-recursive work plus n is bounded by theta of n to the 1. It's just linear. Okay, so then we compute log base 3 of 2, log base b of a. B is 3, a is 2, log base 3 of 2, I just plugged into my calculator, I got 0.63. And just as a sanity check, that makes sense because how many times would I have to raise, what power do I raise 3 to get 2? Well, it's probably has to be less than 1 because 2 is less than 3, right? I'm going to have to raise it by some fractional power. So I get 0.63. Okay, so that's the value, log base b of a. Now what value was c again? Well, c was 1. So that means I know this log base 3 of 2 is less than 1. Log base b of a is less than c. What that means then is we're in that first case of master theorem, that first line. And so we know then our answer is going to be big theta of n to the c. C in this example is 1, and so it's big theta of n. Pretty cool that you could just pop out a number, just plugging and chugging numbers into this formula. And I do want to stress, it is not important and not the point here to understand how master theorem gets the right answer. We're just going to take that as a given. We are going to say master theorem's right, and if it's applicable, if your recurrence is in this form, then we can apply it and come up with the answer by just plugging in our constants. And again, this is one of those things you might be a bit worried there. It's saying, wait, Hunter, I thought you said constants don't matter, which is true. Our constant amount of works don't matter. But the constants that you'll come up with in your recurrences are ones that are all going to matter. They capture high-level information, like how many recursive calls you're making, which is not really ambiguous, and like what you're dividing your input by each time, which again, not ambiguous. So there's no judgment calls on those specific constants, whereas like is a plus exactly one operation or more, that's a bit of a more of a judgment call. Okay, so real quick, I'm just going to throw up this slide. I'm not going to talk about this. This slide is going to walk you through trying to give you some intuition for why master theorem does what it does. We're not going to really it kind of goes into talking about what do these constants A, B, and C represent, like how much you're splitting up the work between recursive calls, how many recursive calls you're making, how much non-recursive work you have to do in each recursive call. A lot of these things, it tries to give you intuitions as to why the answers are the way they are. But again, this is just an aside. It's not the main point of this lesson. So that was our first type of recursive pattern. We said the first type was having the input. And notice for that having the input, we came up with a runtime function using recurrences, and then used master theorem as our asymptotic analysis tool to come up with a bound. So we came up with big theta of something there. And you could see if we actually went through our recurrence we came up with for binary search, you would see that master theorem would tell us that this would just be a log n operation. Okay, so what I want us to, I did not mean to go forward. What I want us to do is talk about the next type of common pattern, which we call constant size input, which sounds a bit weird when you think about recursion at first, but the context I'm going to talk about is this algorithm called merge sort. I want to stress before we go into this. Sorting and merge sort are something we're going to cover in a lot of detail later in the quarter. Right now, the reason I want to introduce this to you is to show you that we can use our tools of recurrences and master theorem to analyze real and useful algorithms. So this lesson, I don't care if you understand how merge sort works. I promise you, we'll get back to it. So don't worry about why is this algorithm doing the thing it's doing. We'll get there. But I want you to relate kind of the big ideas I'm going to be sharing about merge sort with how we can use a recurrence and master theorem to analyze its runtime. Okay? So merge sort is an algorithm for sorting. It's what we call a divide and conquer algorithm, where you take your unsorted array and you split it up recursively into smaller arrays. And then somehow, because you have these smaller arrays, it's much easier to sort an array of size 1 because it's just sorted. And then you merge these sorted arrays together in a merge operation till you get one big sorted array. Again, super fast overview of the algorithm. I'll explain in a future week how this works and why. But the idea is split up work and merge it back together. This is a very brief pseudocode describing how merge sort works. So it's not real Java code. It's just trying to explain the steps of the algorithm. Notice here, this algorithm, this splitting up in half and then merging together, is just a recursive algorithm. So we have some base case and we have a recursive case. Our base case is pretty easy to analyze. It's just an array of length 1 is by definition sorted. And so we just do some constant amount of work to return. And so in our recurrence, we come up with one step if n is less than or equal to 3. Then in our recursive case, we're going to make 2 recursive calls. You can see that here. I'm calling merge sort twice. And on each one, we're going to divide the array in half. So that's why in our recurrence, we have 2 times t of n divided by 2. We do 2 recursive calls, half the input. And then once those are done, we come back and merge. And ignoring the details of how we actually do this merging, I'll just tell you now that takes something like O of n work to go through and merge these arrays together. So our non-recursive work is going to be this plus n. So that's why we have 2t of n divided by 2 plus n as our recursive case. And as a bit of visual explanation walking through this, let me hide my video so we can see the numbers. This goes down and keeps splitting up the array until it reaches its base case, and then it starts merging these together. Okay? So what I want you to try to do, sorry, real quick. We call this a constant size input case because even though we are splitting up the input, the fact that that constant in the front, the 2, and the constant in the denominator, also 2, match, meaning we divide the work in half, but we make 2 recursive calls. We call that overall just a constant size input. At each level of this tree, of these recursive calls, the same amount of work is happening across all recursive calls because we're really not decreasing the size of the input over the whole run of the algorithm. That's a bit subtle, but I wanted to tell you why that was named that. So now what I want you to do is I want you to practice using master theorem to come up with the runtime of this algorithm. So again, understanding the algorithm is not important. The important thing here is I told you this recurrence. We derived this recurrence together. And now I want you to try master theorem to figure out what is the asymptotic bound. So if you need, you could pull out a calculator if you need to compute that log. But I want you to take a second and try this. Okay, so now that you had a chance to try this on your own, let's talk about this together. So in order to do master theorem, you need to compute which constants in the master theorem relate to our recurrence. So we need to come up with those constants A, B, and C to start. So A is that constant in front of your recursive function evaluation. So we have in our context, A is equal to 2 because there's a 2 in front of that T function. So we make 2 recursive calls, so A is going to be 2. B is what we divide n by each time in those recursive calls. In our case, if you look at our formula up top, we're taking n divided by 2. So in this case, B is also equal to 2. And then C is the runtime, the degree of the runtime of our non-recursive work. So we have a plus n here, just like before, plus n is going to be big theta of n to the c, where c is equal to 1. And now we just compute the terms that we need, log base b of a, and compare that to c. A and b are both 2, so if you take log base 2 of 2, it's going to be 1. 1 is equal to 1, right? 1 log base 2 of 2 is equal to c, 1. And so we're going to be in that second case. And the answer there is going to be big theta of n to the 1, or just n, log n. And so we just shown that merge sort's runtime is big theta n log n, which is so cool because we were able to do essentially a proof of its runtime without needing to actually really understand, 1, how master theorem works, and 2, how the merge sort algorithm actually works, because we didn't really talk about merge sort quite yet. And so just as a reminder of where we were, for recursive code, we now have tools that fall under case analysis for our code modeling, which is writing recurrences. And we now just showed how we can use master theorem as part of our asymptotic analysis. So in our next lecture, this is the last video for today. In our next lecture, we're going to talk about one other common pattern, which is what we call doubling the input. And we'll see what happens in this case is what happens when you grow the input each time you make a recursive call. But that's next time. And we'll see in next time another way of thinking about computing this asymptotic result in a more visual way, and how to handle cases that master theorem doesn't actually quite work in. So do remember the big takeaway here was coming up with a recurrence for code and how to apply master theorem to that recurrence to get an asymptotic bound. And in class today, we'll get practice on trying to do these things.